My pleasure to introduce Georg Regensburger today at our seminar. He will talk about Integro-differential operators with matrix coefficients. Georg, please.
Okay, thanks, Gleb. Thanks to the organizers for the opportunity to speak here in this online edition of the Colchin seminar. Yeah, this is joint work with Jamal Hossein-Bor and Clemens Raab, both from the University of Linz, and I'm since October at the University of Kassel in Germany. Good. So you might wonder, I mean, probably many of you have heard me speaking about Integro-differential operators, maybe not so many about operators with matrix coefficients, and why. Before we go deeper into the subject, I want to give the motivation why we look at operators with matrix coefficients. I guess most of you are familiar, or all of you are familiar, if you want to treat linear functional systems of differential or difference equations, for example, we look at the corresponding operator algebras and we investigate matrices or modules over these operator algebras. In particular, so what you see here on the left-hand side, if here we have a system of ordinary differential equations with polynomial coefficients, and this is a specific system, and we look at the corresponding matrix that represents the system and allows us to do algorithmic symbolic computation and algebraic work on this system of differential equations. This is there we consider that we look at matrices to study specific systems. We look at matrices of operators. Now, on the other hand, if we would like to study an abstract or a generic first order system, where we, for example, of ordinary differential equation, where in this case we don't even, so to say, specify the dimension where it lives, we could represent this system by an undetermined matrix A and a differential operator D, and where we really consider this matrix A as a coefficient of this single operator. So, of course, if you want to study specific systems, it makes sense to work with matrices of operators, but if we want to study family of systems, where we don't specify the size, we want to study transformation of such systems, it makes sense to deal with operators with matrix coefficients. And this is what I would like to present in this talk, how we can study and work with Integro-differential operators with non-commutative matrix coefficients. So our original motivation to study Integro-differential operators was coming from, we wanted to work out together with Markus Rosenkrantz and many other people. We wanted to develop an algebraic setting to deal with boundary value problems for linear ordinary differential equations. And this matrix coefficients point of view started with the collaboration with Alban Coindra, where we worked on an algebraic approach to Arnstein's reduction, which is the transformation of a differential time delay equation to a differential equation. And it's an integral transformation. Okay, so in the talk, I would like to speak a bit about Integro-differential rings, always emphasizing also the point, what happens if you have a non-commutative differential or Integro-differential ring. We will discuss how we can construct the ring of Integro-differential operators by generators and relations. And in order to do some symbolic computations, symbolic computation and computer algebra for such operator rings, we would like to give an explicit construction via quotients of tensor rings. And this approach allows us then to study also normal forms and completions of such of the corresponding operator ring. And at the end, I will give a short application to what does it help if we have normal forms in an operator ring. We can prove and discover operator identities, and I will end up with generalization and an outlook. Okay, throughout the talk, I will use operator notation. This turned out to be very useful in this context. So we always omit the parentheses for function applications. And in particular, for example, the Leibniz rule reads then we only need one parenthesis for specifying the Leibniz rule. Okay. Of course, we all know what the differential ring is. It's a ring with an additive operation satisfying the Leibniz rule for all elements in the ring. And we coming with a differential ring, we also always have the ring of constants, just all elements of the ring that are whose derivative is equal to 0. And we also note that it immediately follows from the Leibniz rule that the derivation is linear over the constants. But okay, we write here f and g to remind us of functions, but please also think of f and g as matrices or of square matrices. And usually we are used that the ring itself is constant, and also that the constants are often a field. But if you think of square matrices, the constants themselves become a non-commutative ring. So that's the case if you have the commutative case, for example, C infinity functions, then the constants are just the real numbers, and the derivation is a left k-module homomorphisms. If we think of n times n matrices, the ring is non-commutative, and then the constants become the constant matrices. And in this case, the derivation is only a k bimodule homomorphism. From the left and from the right, we can pull out constant matrices. The ring of differential operators. The normal forms look like usual polynomials, and we have the non-commutative multiplication. We have only a single identity coming from the Leibniz rule. Not completely true. In a certain sense, we have a family of identities. For each element of the ring, we have one identity. They all look the same. Also, the construction works with matrix coefficients. A specific example is the Weil algebra, where we have polynomial operators with differential operators with polynomial coefficients. There we really need only a single identity. And we always write for the operator multiplication a dot in order so that we can always use the same symbol for the operators where we have the symbols, and also for the operations of applying the derivation to the function, so that we can distinguish the two. And here we don't use the parentheses. Again, if the constants are commutative, in particular if they are a field, the ring of differential operators form a K algebra. So we can pull out constants really to the left. But again, if it's a non-commutative ring, the differential operators are only a K ring, because we cannot pull out constants matrices with matrix coefficients. So a K ring, it's just a K bimodule. We have multiplication from the left and from the right, and we have associativity. And yeah, there's of course a big theory on algebraic system theory, where we study linear functional systems, for example, of ordinary or partial differential equations, time delay equations, or difference equations, by studying matrices and modules over such over differential algebras, or more generally over Ore algebras. One other field that is of application of computation with differential operators, or generalization of differential operators, is if we want to do symbolic computations for integrals, sums, and identities for special functions in combinatorial sequences, by computing with the operators that define these special functions or identities. Okay. So this is for the setting of differential operators, and now we would like to extend the ring of differential operators, or the differential ring, with an integration. What are the identities for the integral operators? We have the fundamental theorem of calculus, so that the integral is the right inverse of the derivation, and if we write it the other way, if we look at the identity minus differentiations and then integration, we can also express the evaluation, the point evaluation in the specific setting of for example, smooth functions in terms of these two operators. And the identities that we require, we say, if we have a differential ring with constants k, then we say an integral is a k-linear operation that is a right inverse of the derivation. That's one identity, so that's the fundamental theorem of calculus. And in this specific axiomatization, we require that the corresponding evaluation that we can define, so E is another operation that we can define in terms of, as we said, integration and derivation, and we require that this evaluation is multiplicative, as a true point evaluation would be. Yeah. There are variants of this axiomatization. So we in all these axiomatization, we have the first axiom that the integration is the right inverse of the derivation, but you can weaken the requirement that the evaluation is multiplicative. We can, for example, what Lee and considered with William here together, that the differential that the integration is a differential only is a Rother-Baxter operator, then this structure is called the differential Rother-Baxter algebra. Or you don't impose any condition on the evaluation, then you can look at Integro-differential rings with a non-multiplicative evaluation. That's something that I'm investigating together with claimants. Okay, basic examples. Of course, we can look at polynomials over a field of characteristic 0. We can just define it, for example, integration and derivation and integration on the basis. And then the corresponding evaluation just acts as the evaluating the polynomials at 0. Similarly, you can look at formal power series or a field of characteristics 0. Smooth and analytic functions are, of course, examples of Integro-differential rings. Or also the exponential polynomials are closed under derivation and integration. That's interesting for ODEs with constant coefficients. This is the scalar case, and also we can always look, if we want to have if we want to treat systems, we can also look at matrices of square matrices of such functions. Now we would like to investigate the corresponding ring of Integro-differential operators. So which linear operations do we have? Okay, of course, we have the differential operators. We have the integral, that's another linear operation, k-linear operation. We have the evaluation, and each element of the ring acts as a multiplication operator. And a natural question is, we would like to understand what are all possible relations, all possible identities between these operators, and how do normal forms of Integro-differential operators look like. Again, just the two cases that we studied for a long time was what happens if we have a commutative ring, then all operators are k-left linear. If the ring itself is non-commutative, then the multiplication operators are only additive. You cannot pull out the constant matrices. So that's the difference. And of course, all linear operators with composition form a ring. If the constants are commutative, it's a K algebra. If the constants are non-commutative, it's only a K ring. And so to say, if we are just interested in the definition of Integro-differential operators, and where we can already prove some algebraic properties and see new identities, we can just define it. So the notation that we use, the ring of we start with an Integro-differential algebra with a ring of constants k, and then the notation is, of course, we use the angle brackets for the to see that it, or to denote that it is a non-commutative ring of operators. And we can define it as the ring generated by R. The symbols here they are just symbols for the derivation, integral, and evaluation. And what are the identities that we have? So we have, for every f in f, we have, of course, the Leibniz rule that we've already seen here. So again, the dot represents the operator multiplication, and here we have the operation of applying the derivation to a function. We have the fundamental theorem of calculus. So that's just represented that this product is equal to 1. That's the definition of the evaluation, now written the other way around. And then we have an identity that tells us that the evaluation is commutative. And to reflect that all these operators are k-linear, we know that the symbols for the derivation, integral, and evaluation commute with the constants in k. Okay, these are the 4 defining identities. And now you can, starting from these 4 defining identities, we can look to, do we find other identities between the ring, between these 4 operators? And we already treat these identities, we can interpret them like rules if we use them from the left to the right-hand side. So we always replace the left-hand side by the right-hand side. And then we look at such an ambiguity, the smallest possible situation where we can apply 2 different rules to one identity. So here you can apply on the left first the fundamental theorem of calculus, or here for the product of the second 2, you can apply the definition of the evaluation. We know that this is equal, so the difference must be equal to 0. So we've discovered one identity by looking at this ambiguity. We've discovered the identity that first evaluating and then applying the derivation is equal to 0 makes sense, because the evaluation maps to the constants, and if I differentiate the constant, I always get 0. So this corresponds to the 0 operator. Now this approach, we can look at another simple consequence, or more interesting consequence that we also know is a consequence between the definition of the evaluation and the Leibniz rule. Again, we look at the ambiguity and the corresponding S polynomials. Here we can apply on the left-hand side the definition of the evaluation, and here on the right-hand side for the second factor the Leibniz rule. If you look at the difference, we know that the S polynomial is equal to 0, and we have so to say discovered the following relation between these 2 operators. If we apply this relation to this, so this is identity between linear operators. If we apply this identity to a function g and write it in the standard interpretation of C infinity function, what we get is the familiar integration by parts formula. So this is, so as a consequence of this basic identity, so we discovered, or we regained the integration by parts formula as one of the consequences of the basic identities. So this is, okay, algebraically, this is nice. We can look at, we can construct the ring by generators and relations. But if we want to have normal forms and prove something about normal forms of such operator rings, we need a constructive approach. We need some theory that allows us to prove, to say something about normal forms. And over the last years, what we developed was a constructive and algorithmic approach to rings of linear operators, not necessarily only for Integro-differential operators, but we use this as an example. And we do this via tensor reduction systems for tensor algebras and tensor rings. So this is even more general than dealing with non-commutative polynomials. What are the basic ingredients? The composition of the linear operators is represented by the tensor product. You have seen we have not only one identity, for example, for the Leibniz rule. It's rather a family of identities for every element of the ring itself, and such families of relations can be represented by one homomorphism, by one linear map on the tensor ring. So here, this would be the corresponding homomorphism, or a shorthand notation to represent it on the tensor ring. And the other fact is we will to deal with scale linearity. This is something that we cannot orient. We can always pull out constants or move it from the left to the right. This is why we have to model the ring. This is why we have to tensor over the ring of constants. And of course, for the commutative setting, it's just the usual tensor product over a commutative ring, and the tensor ring itself is a tensor algebra. So this is the scalar case. So so we can really pull out again constants completely with the composition. So that's in the commutative case. In the non-commutative case, if you really want to construct about matrix coefficient, you need to use the tensor product over a non-commutative ring. So here the composition is not bilinear; it's only balanced. You can only move, so to say, constants from one from the right to the left of the other factor, and the corresponding ring is a tensor ring. That's, so to say, the basic data structure. And what we want is, now we want to construct the ring of operators as a factor ring. So we start with an Integro-differential ring, and then the basic operators that we had is the whole ring R itself as multiplication operators, one for one symbol, so to say, where we also can have constant, where we can also have coefficients for the differential operators. Another direct summand are the integral operators, and one for the evaluation operators. And then, so to say, if you want to build up all possible expressions that you can formulate in terms of these operators and composition and addition, all these can are elements of the tensor ring over this K module. So these are all possible. Yes.
Hi, Gil. Yeah, sorry.
Yes.
Yeah, this is Lee.
Hi.
So for this tensor ring, right? Just to make sure. So it still has a linearity, right? So this tensor product. So basically, you have tensor product of with a non-commutative coefficient.
Exactly. I have a
tensor product. That situation.
Yes.
Right? So basically, you need a left module tensor with a right module.
Exactly. All these modules have to be considered as left and right modules. Here, that's a bit. So right, here, right. Here the notation is a bit misleading. You really have to also define a corresponding right multiplications. All these operators are, as you say, bimodules, where you have left and right multiplication, and you tensor over them. Yes, and you can just okay. If you want to have matrix coefficients, exactly. So this is, as we see here, that's what I can do with the constant. Right. You can just pull it from the left to the right in the non-commutative setting. Exactly.
Yeah, but you still have bilinearity, right? Bilinear is still there.
The tensor product itself.
For K. So for K, so for example, if we have two coefficient K1 plus K2, does that distribute when you take a tensor? Yes, right?
Yes,
yeah.
yes.
Yeah.
This we have, yes.
All right.
We still have bilinearity, but we cannot pull out constants. Exactly. Okay, and now if I want to construct the ring of operators, I have to factor out all the identities that I have out of my tensor ring, and yeah, this is the shorthand notation. We factor out all the identities that we get, the four defining identities, or the corresponding ideal in this ring, defined by these identities. And we have two more identities that are that come from the construction. One thing is we have also the empty tensor, which is denoted by epsilon, and we have the one element of the ring itself, and the multiplication by one acts as the identity operator, and the empty tensor acts as the identity. So we have to see that these are one. So we have one additional reduction rule, and also our tensor ring doesn't know about the multiplication in F. So we have to teach it. So if we first multiply with G and then with F, and we do the composition as linear operators, that's equal to the multiplication by F and G. So these are the four defining identities and the two technical identities. And now you can investigate really, now you have really a formal definition of reduction rules and normal forms, because now they operate really on this tensor product. So here that's a very simple ambiguity. Just from the multiplication operator, now we have the product of three operators. Yeah, we can do it first on the left, and the first two factor and the second two factor. So that's a very simple situation. And the difference is the corresponding S polynomial. And now I have to check whether I can reduce this S polynomial to 0. So what I have to do is I can apply the rule again. And at the end here, it is very simple. I have an identity in R, and all that I need to see that this identity reduces to 0, I need associativity in the ring R. This tells us that this specific S polynomial reduces to 0. And more generally, one can say an ambiguity is resolvable if all S polynomials can be reduced to 0. And then there is the diamond lemma in this full generality. It was already presented by Bergman over a so you can deal with tensor rings over a non-commutative ring. So given as such a tensor reduction system, every tensor has a unique normal form if all ambiguities are resolvable. So if all S polynomials reduce to 0, and in this case, we know how the normal forms of the factoring look like if the tensor ring factored by the reduction ideal is then isomorphic to the ring of irreducible tensors, the ones that I cannot reduce anymore. And we have generalized this a bit to deal with the current situation. We have introduced specialization, so we can also have that these reduction rules have overlapping domains and things like that, and we've implemented it. And or Clemens has implemented it. And if you do this, you can also do, not fully automatically, but you can have a completion process. You start with defining identities, and each time you have an S polynomial that does not reduce to 0, you discover a new identity. You can derive additional identities. And then at the end, you can also investigate all possible, so to say, of all possible ambiguities. And if you can show that all of these ones reduce to 0, you know normal forms. And this is, so to say, here you see the family. We have the defining identities and all possible consequences, some of which we have already seen. And in order to prove that these are all identities that follow from the Leibniz rule and the fundamental theorem of calculus, you have to show that all S polynomials reduce to 0. So here that's already, without computer support, it would be a long task. There are already 52 ambiguities, and with shorter and longer computations, you can really show that all of them reduce to 0. The nice thing is, this works also for matrix coefficients, so also in the non-commutative case, and we rediscovered the normal forms that we had already in the scalar case, also in this generality. Yeah, you see in a certain sense that all these rules simplify something. The length of the tensors become shorter, and you can prove that the normal forms look like this. You have the differential operators, the usual differential operators that we know. All integrals reduce to a single integral, But here you have a factor on the left and on the right, and then you have also tensors representing, so to say, u prime at 0, or initial conditions plus a factor. These are all irreducible tensors. And to show you a short application, what you can do with this. So this is, the proof really needs computer support, or it's very helpful to have computer support. But once we've proved it, we can use the normal forms, and we can also investigate as a simple example to see the usefulness of matrix coefficients. We would like to prove here a well-known formula, the variation of constants, but for a generic system. We don't specify by a single short computation in a ring with matrix coefficients. So we know that for first order systems. Now you can represent this, the equation, by a single linear operator with matrix coefficient, and so to say the variation of constant is then the given by the operator H, where here we can, so to say, just join a fundamental matrix. That's all that we need to know here. It's an element of our ring that is invertible and that satisfies the differential equation. And then if you want to show, prove the variation of constants, we just do the computation here in the ring of operators. Now we write it again just with the C dot as the multiplication, not with the tensor symbol. Here you just apply the Leibniz rule and use that phi is a fundamental matrix. And then variation of to prove that this is really a solution of the differential system that corresponds to this computation in the ring of Integro-differential operators. Here we use the first identity, then we use the Leibniz rule, and then we use the product that this is equal to 1. And this is the proof of variation of constants. For a system of generic size, we don't need to look more into the system, but we need to have that we are working in a non-commutative ring, and that our operator ring is really of this non-commutative ring. Of course, if you have normal forms, you can also solve or discover operator equations by making an ansatz. So suppose we wouldn't know variation of constants, and we want to find such an operator H. We can make an ansatz because we know the normal forms, and one easily sees that one doesn't need a differential term if we want to have the right inverse. So you could make a longer ansatz, but now we reduce it to this specific case. So it has to be a differential operator with two undetermined coefficients. Then we compute the normal form of L times H with this undetermined coefficient. We do the computation in the ring of operators, and then we can do coefficient comparison. So because we want this to be the identity operator, so we find by comparing coefficients, we find that H2 must be a right inverse of H1, and this term should vanish. So we see that H1 should be a solution of the differential equation. And now we can, so to say, solve it, or at least algebraically. We just join an invertible element that solves the differential equation, and then we find the usual formula for derivation, for integration, for variation of constants. And of course, this can be applied more generally to more general operator identities and equations where you don't know the answer, or where it is more complicated to see the answer. And what you get for the coefficients is usually a system of integro-differential equations here. So this approach, I mean, here we've seen it now for integro-differential operators, but as soon as if you can find and prove normal forms and do this completion process, you can do effective computations over other operator rings. You can prove identities. You can solve equations by ansatz. We've done this for a few other generalizations or systems of linear operators. In particular, we wanted to have also the delay operator to deal with linear differential time delay systems. So what we did, we had to model linear substitutions and axiomatize, and then develop a confluent reduction system. Here, these are then 21 rules, so it becomes more complicated. But with this system, we could deal really on the computer with the Arnstein transformation, which was our original, one of our motivations to study operators with matrix coefficients. Okay, so I think I have still a few, 2-3 more minutes, or yeah, okay, good. So of course we can, if we have time afterwards, or if someone is interested, we could also have a look at the file to see the proof, for example, how these normal forms can be proved, or that all S polynomials reduce to 0. And another generalization that I mentioned already at the beginning is what happens if we have, so to say, non-smooth or functions with singularities. Then we cannot really evaluate them at the point. The simplest examples would be Laurent polynomials. You can make the Laurent polynomials into an Integro-differential ring by defining the integral just by integration by parts. And if you do this, you find that the evaluation then acts as evaluating the constant term of this Laurent polynomial. And of course, this evaluation is not multiplicative anymore. Yeah, of course, for example, if I take the function x and 1 over x, the product is equal to 1. So the evaluation of the product is equal to 1. But x has no constant terms and 1 over x has no constant terms. So the individual evaluations are equal to 0. So this, if you want to have a multiplicative evaluation, which is nice for boundary value problems, it's not good for what we are often used to work with, for example, rational functions or generalizations. You can never have a multiplicative evaluation. So we have to give up this axiom. And then you can look at generalized Integro-differential rings where you don't require the multiplication to be multiplicative anymore. And yeah, we have now quite a comprehensive study, or yeah, we've investigated these rings. We've investigated how product of nested integrals look like, generalized Taylor series, initial value problems for such settings, and we've also investigated the corresponding ring of operators together with Clemens. Yes, so that's another generalization. And what, yeah, okay, here as an example that it is useful, so to say, to compute with operators with matrix coefficients to deal with systems. Now we can, with this approach, we can study families of systems and transformations of such linear functional systems by studying the corresponding operator rings. What we've also already done is we've looked at, for example, discrete analogs of our operator rings. If you have the difference operator and partial summations, the identities become more complicated. There's some new phenomena appear, but also there we have normal form, or for some classes, we have normal forms for the Integro-differential operators. Here we always assume our operators to be square matrices and to form a ring. Sometimes it also makes sense to have, or it often also makes sense to have rectangular matrices. Then the ring structure is not, yeah. We've investigated this case. What happens if you also want to deal with operators that have domains and codomains, and develop the approach there. And so to say, on the ring itself, what happens if you start with a differential ring and you want to have the to build the corresponding, or you want to construct an Integro-differential ring starting from a differential ring, you have to deal with nested integrals, and you have to have normal forms in order to study on such. You have to have normal forms for nested integrals, and that's another direction of research. Okay, thanks for your attention, and I'm happy.
Thank you, Georg. Thank you, Georg. Let's thank the speaker. Or maybe like more in German style. So yeah, please, questions to the speaker, please unmute yourself and ask, or type into the chat.
I would like to ask a question. I'm interested in the question of what the integral operators might be on the matrix ring. So if just to make up an example, if we start with the matrix ring over constants, we make it a differential ring by using an inner derivation by a fixed matrix. Are there any integral operators associated with that?
Okay, so we started from the standard example from for example the infinity functions or smooth function and just component-wise integration, and you are now asking if we start with
No, actually it's related to what you just said. So I was curious about whether there were examples of matrix differential integral matrix rings that where the integral didn't come from the coordinate-wise.
Coordinate-wise integration. Yeah, that's in a non-commutative setting. Let me. Yes, now at the moment I don't know an example, or we have not really, because that's a very interesting question, because yeah, we came, so to say, from the concrete application where it's completely clear how this is done, but yeah, that's an interesting question.
Oh, okay, good, because I couldn't think of an example, so
yeah.
Thank you.
Okay, thank you, good. So but there should be examples, I hope. Okay.
Other quick question?
Yeah.
Hi, please.
Yeah. So it's Leo again. So
hi, Lee.
Right. So with the normal form, so may one say that more or less you give some kind of normal form of this integral differential equations with non-commutative coefficients. So in other words, if you have, if you randomly choose integral differential equation, right? So,
yes.
And then some of them may be the same, right? For example, by Leibniz rule or whatever. So the way you describe, you have normal form. So can one regard this as that, any integral differential equation would be reduced to exactly one of these forms?
Yeah, if you have a linear equation, yes, you can really reduce it to normal forms and then decide whether the two are equal, except of course that you have to be able to decide equality in the ring or itself, so to say, in the ring R itself.
Oh. Yeah. You have to decide which two elements are the same in the ring, right?
Which two elements are the same, and exactly. This is of course left to do.
Yeah.
But,
okay.
Yeah, you have more time. So in a certain sense, everything that follows just purely algebraically from the fundamental theorem of calculus follows can be shown by applying the rules in any order. Because you always end up in the same normal form, except, of course, for deciding equality in the ring itself.
Yeah. Okay. So regard this this work, it's very nice. So maybe I can mention these two papers that in the past related. So one is a paper with Marcus and Xingao, where we actually construct this ring of differential rota-based operators. You mentioned this differential rota-based algebra,
yes.
Right? So we consider, of course, this setting is different. Also, we consider the commutative case. So it's we construct this ring of differential rota-based operators.
Exactly.
In your case, it's the ring of integral differential algebra, right? So the axioms are different, and also you consider non-commutative. So in that paper, it's commutative. So it was published in 2018. Another paper is a recent paper with Richard Gustafsson, who is here, and Yunnan Li, where we consider this integral equations. We consider this actually separable integral equations. So there we also obtain some kind of normal form. So it's so the integral operator is more specialized, but then the kind of normal form is kind of smaller. Well, yeah, but it doesn't consider the differential part. So
okay.
Yeah, it doesn't consider integration differential part. So yeah, I just want to mention this. So yeah,
these two examples. Yeah, thanks a lot. These are other
right.
important examples, so to say, of operator equation rings of operators that one can investigate. And a small change in the of course in the axiomatization can also result in a big change in terms of the normal forms and the corresponding computations. And
yeah, so overall in recent years there have been a lot of interest on these linear operators, differential, rota-based or integral. That's just two of them. There are other operators like Neinhaus and that William and I and the co-authors, we consider a whole family of them. So there is actually some kind of a classification. So right. So I'm just saying that overall, the study of this linear operator is getting very, very interesting. One part is like what you are doing for symbolic computation. Okay. So very nice. Yeah. Thank you.
Thanks a lot for these remarks and pointers to related work.
Do you have some questions right now? Okay, then we'll continue to the breakout room.